Well, how do we go from these past events to current? I've told you that if impacts happen in the past, they can happen in the future. And indeed, you can get a very good perspective on how frequent impacts are, not by looking at the Earth, but the Moon. You've all seen the Moon through a telescope or pictures. There are 30,000 impact craters on the near side of the Moon that can be seen with even a small telescope. And the Earth and the Moon have lived together for 4.6 billion years. So the Earth would be just as heavily cratered as the Moon if we didn't have geological and erosive forces to erase the craters. We have been hit over and over and over. And that will continue in the future. It's not something limited to the past. When some of us began to point this out in the 1980s, we were largely influenced by that impact 65 million years ago. I mean, that, as I say, was revolutionary. That changed our perspective and made us realize these things could happen today. And even an impact that is minor on the scale of the planet can do an awful lot of damage. That end Cretaceous impact, I said, was a 15-kilometer diameter object. That is less than 1/10 billionth of the mass of the Earth. An impact like that has no effect on the Earth. It doesn't change our orbit, our spin, our magnetic field. To the Earth, it's just a pinprick. And yet it was enough to produce a mass killing. And so we suddenly became sensitive to this idea and went through the thought experiment to see if this was a contemporary hazard. And I talked to the Congress about it. And I think this, from 1991, is a very good statement of the problem. And what the committee said is the chances of the Earth being struck by a large asteroid are extremely small, but because the consequences of such a collision are extremely large, the committee believes it's only prudent to assess the nature of the threat and begin to deal with it. And that's what they asked NASA to do, and I had the good fortune to chair the committee that studied the nature of the hazard and what we could do about it. Just to show you the kind of objects we're dealing with, this is the largest of the near-Earth asteroids. It's about 30 kilometers long, so it's as big as almost from here to San Francisco, as that end of the part of the bay. And it's irregular and heavily cratered and rocky, and certainly an interesting object. But don't think of these as round bullets; they aren't. This Eros we studied in great detail. A NASA spacecraft went there, orbited it for a year, and then landed. At the other extreme, the small objects, this one is about as big as just the central part of this campus. And it was visited 2 years ago by a Japanese spacecraft, Hayabusa. And it's called Itokawa. I think there's some more than a coincidence here that the Japanese chose to go to an asteroid named after a Japanese scientist. But it's much smaller. And if you think about it and compare to that last one with craters, you'll notice there's no craters here. It's only lumps. Some very different process. These are the size objects that are by far the most likely to hit us. There are many, many more small ones than large ones. Eros is bigger than the asteroid that did in the dinosaurs. Fortunately, it's not scheduled to hit the Earth anytime soon, if ever. But a little one like this can come along any time. And don't kid yourself that there are a bunch of astronomers out there staring at the sky waiting to see one coming. Without the kind of survey, which I'll discuss in a minute, the average warning that you will have of an incoming asteroid is about 5 seconds. The first you'll know is when the sky lights up and then the ground shakes. There won't be anybody seeing it on the way in. Well, one way to look at this is to estimate the frequency of impacts and get some idea from that about what we should or shouldn't worry about. And this is my only graph. Stick with me for a minute. I want you to be able to read it, but then we won't have to look at it anymore. What I've plotted here are the size of the impact. And now this isn't the diameter of the asteroid. This is the energy. And for energy, I've used megatons, the unit we all are familiar with in talking about nuclear explosions. The Hiroshima nuclear blast was down here. The biggest ever done, the Russian one, was here at about 65 megatons, and then it goes on up from there. On this side is the average interval between impacts that size. And very conveniently, that almost lies on a perfect straight line. The end Cretaceous, and I apologize, we don't normally spell Cretaceous with a K, but the Germans do. And that's why it's called the KT, the Cretaceous Tertiary. It is 100 million megatons, 100 million tons of TNT. The Tunguska that I told you about, the beginning is about 15 megatons. And you can look at the frequency. The KT is going to happen about once every 100 million years on average. A Tunguska once every 1,000 years on average. And so you can predict, in a sense, what the statistical risk is. If these just come randomly in time and you can't predict it, then you can ask, well, what is the chance that it will happen this year? Or you can even estimate how many people will die in each one of these. And I could look at Edna and say, what is the chance that it will say on your tombstone that you died from an asteroid? It's more than zero, unless you're planning to get your tombstone carved today. Because there's no warning, remember? When Clark Chapman and I first put this together, it was interesting because we carried the curve up and looked at how often there should be a blast the size of the Hiroshima atom bomb. And you can read from there, it's about once a year. And we had one of those moments in science when you think you've really screwed up. And you think, well, maybe I made some huge arithmetic error. Because we said to ourselves, if there were something as big as the Hiroshima atom bomb going off on Earth every year, wouldn't we have heard about it? Wouldn't we read about it in the papers? How could this be hidden? And then we did some more calculations and realized that things that size explode as soon as they hit the atmosphere. 50, 60, 70 kilometers up. And the shock wave never reaches the ground. But how could we verify that? Well, we were fortunate. We did this work in about 1991 and 2, at the end of the Cold War, when the Air Force and the agencies that deal with national security were getting a little more open. And we realized that there were large numbers of down-looking satellites, surveillance satellites, using infrared and visible, looking at the Earth, that ought to see the flash of light when one of these impacts takes place. And we got to go down to what was then Falcon Air Force Base, now Schriever Air Force Base, the head of the Space Command, and talk to the people. And they said, sure, we know about those. We asked them, have you received any big flashes? They said, yeah. They said, do you know what they are? Sure, they're meteors. And they said, we've known that for 25 years, and we've built our software to exclude those because we know they're not enemy weapons. And so they don't bother us, and we don't even keep very good records of it. But there were enough records, and now there are better, to verify that that is exactly right on the curve, that there is something as big as Hiroshima about every 6 months. And these days, the Air Force puts out a press release once or twice a year telling about those. Well, as I said, I can calculate the statistics. That, by the way, came out very shortly after Katrina and the FEMA activities. I could calculate probabilities. I could calculate frequency of impacts. I could calculate where the risk lies. I can tell you, for instance, that you're more at risk from an asteroid 2 kilometers across than from one that's either larger or smaller. But in fact, that is not what most people want to know. They are not really interested in the probabilities, which are low. They want us, the scientists, to tell them when and where the next impact will take place, to discover the object before it hits.